it's a pleasure to be here to announce our Pedro Nunes Lecture of 2025. Okay, so the Pedro Nunes Lecture is an initiative of CMUP together with SPM, Portuguese Mathematical Society, and the main goal is to bring to Portugal high-profile mathematicians. Okay, so this year we have the honor of having Michael Christ with us, and I'll just read you the introduction you could have seen in the posters outside. Anyway, just make a brief introduction of Michael. Okay, so Michael was born 7th June 1955. Is an American mathematician and emeritus professor at the University of California, Berkeley. His research has Fourier analysis at its core and encompasses partial differential equations, complex analysis in several variables, and topics in mathematical physics. Among his many outstanding research contributions, we highlight the definitive analysis of global regularity of solutions of delta bar problems on pseudo-convex domains, the proof with Collier and Tau of the ill-posedness of low regularity solutions on the nonlinear Schrödinger equations, and characterization with Kingsley of the absolutely continuous spectrum and generalized eigenfunctions for second order ODE with potentials on the real line. Michael has been an invited lecturer twice at the International Congress of Mathematicians, first in Kyoto in 1990 and then in Berlin in 1998. He has received numerous honors and awards, including an NSF Presidential Young Investigator Award and a Sloan Fellowship, the Bergman Prize from the AMS, and a Miller Research Professorship. He was elected to the American Academy of Arts and Sciences in 2007. So thank you very much for being here, and it's a pleasure.
Thank you for the kind introduction. So I'm delighted and honored to be here. When I thought about these lectures, I felt that I should do something broad, and I realized that there's a theme which has been struggling to emerge in my own work over a period of some 25 years or so. And so I'm going to try to bring that theme out and illustrate it through various bits of my work. So we start with, the title says multilinear oscillatory integrals, and I'll say what's meant by those words. We start with oscillatory integrals, and we start with a very simple kind, the scalar oscillatory integrals. So these are expressed as integrals. I have written two versions here. So in the first one, we're integrating over a ball. It's always a bounded region that we're integrating over, or almost always. And we have an integrand which takes the form e to the I lambda phi. Now, lambda is going to always be a large real parameter. We're interested in what happens as it tends to infinity. Phi is called the phase function. Phi is always going to be very smooth and real valued. So the integrand here has absolute value 1 at every point. We think of phi as given and the integral as what comes out, and we want to understand the integral in terms of phi. An alternative version, we integrate at least formally over the whole space, but we have a cutoff function eta here, which is not important, but which does have compact support. It's very smooth, and so that effectively, again, restricts us to integrating over a bounded region. And we have the important part, the same e to the I lambda phi. Okay, we're interested in asymptotics or bounds as lambda tends to plus infinity. These will depend on the nature of phi. There's no one answer, but it depends on the properties of phi. And so we want to see how properties of phi are reflected in these asymptotics or upper bounds, not lower, but upper bounds. In practice, one is interested not just in having a one-parameter family of things, but rather one might have a finite vector space, finite dimensional vector space of functions phi, and then the norm is going to go to infinity. Or one might have some even larger class that's not a finite dimensional vector space at all. Okay? So to some extent, this large parameter lambda is really a stand-in for something more general. But this is enough usually to illustrate the themes that one is interested in. Okay. So one of the main ideas here is the principle of stationary phase, which says, first of all, that if the phase phi has no critical points, so if its gradient vanishes nowhere, then the integral decays very fast, faster than any negative power of lambda. Okay? If phi does have a critical point or several critical points or even a whole manifold of critical points, then the rate of decay is governed by the asymptotic behavior of the gradient as the set of critical points is approached. Okay? This behavior is typically understood in terms of higher derivatives of phi. So one might have a hypothesis that some second derivative, some perhaps second partial derivative, or some third derivative is non-zero, that maybe several derivatives are non-zero, that some combination of derivatives is non-zero. A standard one is the determinant of the Hessian matrix of second derivatives, for instance. Okay? So there are various ways one can formulate these things. There's a very good theory in dimension 1, everything if one is integrating over a one-dimensional region. There's a reasonably complete theory for R2 due to Varchenko in the 70s, but already in dimension 3, there's no completely general theory that tells you what sort of answer you have for a given phi. So this gets complicated pretty fast. Sorry, I have to keep switching between these two controls. Okay, but what we're going to be interested in are not scalar oscillatory integrals, but operator oscillatory integrals. In this talk, so an operator takes in a function and spits out a function. We're talking first about linear operators, but in this talk, I'll usually view linear operators as bilinear forms. So I'll take the output and pair it against a function. So my linear operators, really bilinear forms, will take in two unrelated functions and spit out, in a bilinear way, spit out a complex number. Okay? And so we're interested in the following kind of thing. First of all, the formulation is written like this. We have our phase function, which now depends on two variables. We have two general measurable functions, f and g, and we never assume any smoothness on these. These are always just measurable. If they were smooth to any degree, we would simply put them in with the cutoff function, and we wouldn't really consider them the things the operator acts on. So we're interested in the interplay between the oscillation in this factor and these measurable factors, and in this case, the fact that one depends on x and one depends on y, but we're not assuming we're not allowing any assumption of smoothness on them. So we want to find an upper bound for this in the form of a product of Lebesgue norms, LP norms, of f and g, maybe with different exponents, and we want typically a negative power of lambda. So as lambda tends to infinity, such a bound says that this tends to 0 at some reasonable rate. Okay? Eta in this setup is always smooth and compactly supported, and it's relatively unimportant. It more or less just specifies the region that one is going to integrate over. Okay? The most important example is phi of xy is the inner product of x and y. In that case, when the exponents p and q are both 2, the inequality holds with the exponent dimension over 2. We're integrating over RD cross RD. The inequality holds with an exponent equal to the dimension over 2 and no better exponent. And this is actually equivalent to Parseval's inequality, which just says that the Fourier transform maps L2 to L2. You can make this integral over a bounded region enforced by the cutoff function into a global one by just dilating, and when that happens, the power of lambda plays with the dilation parameter. So this is really equivalent to Parseval's inequality in this form, and this sort of basic example was generalized by Hormander, and then that many other authors went much farther. Okay. All right, so oscillatory integral operators are widely seen in the theory of wave phenomena, in the solutions of various partial differential operators and related things that describe wave behavior. To illustrate this, I've picked one particular one. This is a dispersive equation. It's Schrödinger's equation. So square root of -1 times the time derivative is equal to the spatial Laplacian of u, and there's an initial condition u is specified at time 0. And then there's this integral that gives you a solution. You integrate the Fourier transform of the initial data, f hat, times e to the I x dot c plus t times modulus of c squared. So here's our oscillatory factor, and it doesn't just depend on a single large parameter lambda. There are really two parameters here. There's the time t and the spatial variable x, which is itself as a vector. But you see here that if either the time is large or if x is large, then this e to the I factor is rapidly oscillatory. Okay, so that's a concrete example of how an oscillatory integral operator actually arises and is used in practice. Okay, there is a go-to device for proving upper bounds for oscillatory integral operators. this is what any expert or any well-trained graduate student would try on anything where they didn't already know the answer. So this is really the go-to device. Many linear operators, and now I've written this as an operator, not a form. Many linear operators can be written as integral operators. So Tf of x is the integral of k of x comma y f of y dy. K is sometimes called the kernel. And the method is to compose this operator T with its formal adjoint. So you consider T composed with T star, and that can also be written as an integral operator. And there's a formula for the kernel that's attached to that operator. It is the integral of k of x z, k complex conjugate of z comma y dz. Okay? And when you do this, and this will be very important later in the talk where it will not work, when you do this, two good things happen. First of all, in the inner integral, there are no general measurable functions. The f and g are gone. Okay? So we have this method turns an operator oscillatory integral into a scalar one, which is typically much simpler. And second, well, I just said it, what's inside, if k is rapidly oscillatory, then there's rapid oscillation in here. So to understand this integral, what one needs to do is have a very robust version of the theory of scalar oscillatory integrals. Okay? So the theory of operator oscillatory integrals is built on the theory of scalar ones. And one really needs a robust theory because the kernel, the parameter here in really is x comma y, and typically it's highly oscillatory for some and not for others, and there are all kinds of degrees. It's certainly not a one-parameter situation. So one needs a robust theory of scalar oscillatory integrals to make progress here. Okay, so I'm going to first give you one concrete example of how, in practice, multilinear oscillatory integral operators arise and are useful. Nonlinear operators can sometimes be analyzed by expanding them into multilinear ones, just as smooth scalar valued functions can be productively analyzed by expanding them in Taylor series in powers of a variable. So we're going to consider a problem of ordinary differential operators or equations. This is the generalized eigenfunction equation. It is posed on the entire real line. It'll be important for us that it's global because we'll be interested in the asymptotics as x goes to infinity. Here we have a Schrödinger operator, minus d squared dx squared plus v. And v is an operator, but it also is a function. So the operator v is multiplication by the function v. Okay? So this is a Schrödinger operator. It's a time-independent Schrödinger operator with the potential v. And this is formally an eigenfunction equation. It says that the operator applied to psi is equal to an eigenvalue, which I call lambda squared, times psi itself. Okay? It's a generalized eigenfunction equation because we'll be in a situation where the solutions are not square integrable. So they're not entitled to be called eigenfunctions. But algebraically, it's an eigenfunction equation. And it's just for algebraic reasons that I've chosen to write lambda squared instead of lambda. Okay, we make the potential real valued, so this is at least formally going to be a self-adjoint operator. Okay, all right. Under very mild assumptions on V, global solutions exist. It is a linear ordinary differential equation. If V is merely integrable on every bounded set, then a global solution will exist. And the question here is how they behave as x tends to infinity. Okay? This problem is related to the problem of understanding the spectrum of this formally self-adjoint operator, whether the spectrum is absolutely continuous or has an absolutely continuous part. So how does psi lambda behave as x goes to plus infinity? Okay? The question of how behavior at plus infinity relates to the behavior at minus infinity is scattering theory, and I'm not going to go that far in this theory. So we're just going to let x go to plus infinity. Remember that when v vanishes identically, the solutions are linear combinations of e to the plus or minus I lambda x. Okay, that formula will be important for us in a second. Okay. All right. There is nonlinearity here. The equation for psi is linear, but there's also an operator here. It takes in the potential and spits out the generalized eigenfunctions. And the behavior of the psi on the potential v is highly nonlinear. Okay? So really, that's what I want to get at. I want to understand that nonlinear operator, the one that takes in the potential and spits out the nonlinear, the eigenfunctions, the generalized eigenfunctions, which depend on x and lambda, and of course, on V. Okay, so here's a theorem about this due to Kiselev and collaborator almost 25 years ago. We have an exponent p which is between 1 and 2, excluding 2. We have a potential which is the sum of a relatively trivial part in L1 that's globally integrable, and another part which is in LP. So a typical function that satisfies this would be something that goes to 0 like x to the minus 3/4 or x to the minus 2/3. Faster than x to the minus 1/2, but it doesn't have to be integrable. Okay? All right, and the theorem says that for almost every spectral parameter in the sense of Lebesgue theory, the generalized eigenfunctions, the solutions of the ODE, are globally bounded. They don't just exist, but they're globally bounded, and they have asymptotics. There's a remainder that tends to 0, and there's a main term which looks like e to the I phi, where phi is given by this concrete formula. It's lambda x, which is what you get when the potential is 0, and there's a long-range correction term which is proportional to the indefinite integral of the potential itself. So under these hypotheses, this indefinite integral can go to infinity, but slower than linearly. So this is a lower order correction term. Okay? Now, of course, it's a two-dimensional equation. There's a two-dimensional space of solutions. And the precise statement is there exists a linear combination of those two, which has this asymptotic behavior. The complex conjugate is also a solution, and that gives you two solutions. Okay? All right. So that is the theorem. And that theorem was proved using an expansion in terms of multilinear operators. So these are the multilinear operators that arose. There's one for each positive integer n, and it is an n-linear operator. So it takes in n different functions f, and it spits out a function of the spatial variable y. That was x on the last slide. Now it's a y, and the spectral parameter lambda. And there's an integral over a complicated region, which I'll get to. And the integrand is a product. There's one factor for each of the f's. There's one variable of integration for each of the f's. So it's an integral over an n-dimensional space. And there are n oscillatory factors, e to the plus or minus I times 2 times the phi lambda. That was the lambda x with the long-range correction on the last slide. Okay? So that is an oscillatory factor if you put those n things together. And it's an integral over a high-dimensional space, and it takes in an arbitrary number of unknown functions f. The domain of integration is a kind of upper diagonal space. Given y, you integrate over all x1 greater than y, all x2 greater than x1, and so on, all the way up to the last variable xn, which goes all the way out to infinity. Okay? And the solution of the ODE can be formally expressed, and it was proved that it can really be rigorously expressed, as a sum of an infinite series where the first term is the asymptotic term that I told you, and all the higher order terms are products of that asymptotic thing. There's actually a plus or minus here. It alternates. It's not important for us. Times the output of these multilinear operators, where you take each of the f's to be v. So this is a little odd. You apply this operator, its definition itself depends non-linearly on v, because v enters into these things, but then you also specialize to where the f's are equal to v. So it's sort of a hybrid thing. It depends non-linearly on v, and it's a multilinear operator acting on copies of v. Okay, so none of this is terribly important for the rest of this talk, but this is supposed to illustrate that multilinear oscillatory operators of arbitrarily high order really arise in the solution of a completely concrete problem. Okay? All right. All right, so now I'm going to change gears and start with some very simple things. The next theorem I'm going to tell you is, I think, not really an important one. I don't know any real applications for it, but it's supposed to show that the multilinear world is the world of multilinear oscillatory operators has phenomena that you don't see in the world of linear multilinear oscillators. And this is the simplest illustration of that I know. So a very fundamental multilinear inequality says that convolution maps L1 cross L1 to L1. If you convolve a function in L1 of an abelian group with a function in L1, you get a function again in L1, always with respect to Haar measure. Okay? So in particular, if you have an interval, I'll just take a bounded interval in the real line for simplicity, and two non-negative integrable functions, then this integral, integral of f of x minus y g of y dy, is finite for almost every x. In fact, this integral defines an integrable function, and integrable functions are finite almost everywhere. So I want to ask what happens if we put in another factor. We make it trilinear instead of bilinear. So I'm going to take the third factor. We have a third arbitrary function h, and we're going to evaluate that at x plus a constant times y. So we now have x minus y, we have y, and we have a third linear function, x plus alpha y. And I want to avoid degenerate cases, so I'm going to exclude two values of alpha. Not important, just ignore them. Okay, so question. If we put in three arbitrary non-negative measurable functions, what amount of integrability do we need to assume for them to ensure almost everywhere finiteness of the integral? Okay? Now, I'm not being very ambitious. I'm not asking for L1. I just want the integral to be finite almost everywhere in the sense of Lebesgue theory. So I'm going to assume each of these is in a Lebesgue class LP, and I'm going to ask how big do I need to assume P to be to ensure that this integral is finite? Okay? Very, very, very simple question. The bigger P is the better. So the question is, how far down can you push P? The obvious threshold is P equals 3 over 2. If you take the bilinear result and you use Holder's inequality and changes of variables, you find that P equals 3/2 always works. Okay? So question, can you go below the trivial exponent 3/2? Well, you can if and only if the parameter alpha is rational. So remember the alpha. Let's just go back. Let's go back using the correct control. So here was alpha. Alpha was the coefficient here. And the theorem says you can go below the trivial exponent 3/2 if and only if alpha is rational. So this is something which just doesn't have an analog in the theory of bilinear things, the theory of convolution-like objects. This is something new for the trilinear operator. The proof for alpha there's an interesting connection here. The proof for rational alpha relies on a generalization of an algebraic device that was introduced by Gowers. He was interested in quantitatively improving something called the Balog-Semiretti lemma, which is something in additive combinatorics. This was his work on Semiretti's theorem. And he wanted a quantitative improvement on a combinatorial lemma. And it was later adapted by Bourgain, and then his idea was improved upon by Katz-Tau to make some progress on the Kakeya problem, something in geometric measure theory, in high dimensions. To me, a very unexpected connection. The negative result, the fact that you can't improve the exponent for irrational alpha, has to do with the classic fact about Diophantine approximation of irrationals by rationals. Every irrational can be written as P over Q plus O of Q to the minus 2 for an infinite sequence of denominators Q, and that is used in the negative result. Okay. For almost everything I'll say in this talk, there are lots of open questions. Here, open question already, what happens with 4 factors? What happens if you add another alpha and the 2 alphas are both irrational? I don't know. So this is something very simple but already wide open. Okay. One of my themes today is that intricate algebraic phenomena lurk just below the surface in the theory of multilinear operators and forms. And I'll next illustrate this theme with a brief discussion of what are called Holder-Braskamp-Lieb inequalities. Unlike the last bit, these inequalities are a success story. A lot is known, but I'm going to show you a subtlety which may be slightly surprising in that theory. Okay, so Holder-Braskamp-Lieb inequalities. Here there's no oscillation. We have an integral over some whole Euclidean space. There's no cutoff function here. The integrand is a product of functions composed with mappings to a lower dimensional space. So each factor by itself sort of depends on fewer variables than the total number of variables, but they all do that in different ways. Okay? Linear ways, but all in different ways. We want to majorize such an integral by a finite constant times a product of Lebesgue norms. we want to be generous and allow all kinds of different Lebesgue norms. We're not prejudging and choosing L2 norms or L1 norms. Okay, so again, the LJs are linear mappings, surjective for technical reasons, to a lower dimensional space or spaces. The dimensions of the targets can be different. The functions are non-negative, they're measurable, but they're otherwise arbitrary. Okay, and we want to know when is such an inequality true. There are some basic, very, very basic inequalities that fit this scheme. One is Young's convolution inequality, which says that if you take a function in LP, convolve with a function in LQ, you land in LR for a certain exponent R, which depends on P and Q. I've written that as a bilinear form here. There's the Loomis-Whitney inequality, where you are integrating over RD, and what you do is if you have D variables, you can forget one of them. And then that gives you an element of RD minus 1. There are D different coordinates, so there are D different mappings from RD to RD minus 1. You take all of those D mappings, and for each one of them you put in a function. So pi j is just the projection that forgets the jth coordinate. And there's a bound for that in terms of certain Lebesgue norms of the FJs. That's called the Loomis-Whitney inequality. It's sort of related to the isoparametric inequality. So it's another very basic, commonly occurring inequality. Okay, all right. So the first question in Holder-Braskamp-Lieb theory is the mappings LJ are regarded as given, and we want to know for which exponents the inequality is true. That is, for which exponents Pj does there exist a finite constant for which the inequality holds? Okay? There's a whole theory about what that constant is equal to, but I'm not going into that today. For us today, the question is just, when does it hold with some finite constant? Okay, now there are also discrete analogs where you replace the vector space RD and the linear mappings LJ by finitely generated abelian groups, so discrete groups, and you take group homomorphisms to other abelian groups. Okay? The integration then is just with respect to counting measure. You just add over the elements of the group. Okay? All right, so there are discrete analogs as well as the continuum version. Okay, so here is a theorem which answers this question about when the inequality holds. It was proved in two versions in the years indicated by Bennett, Carberry, Tao, and collaborator. And the theorem says that the inequality holds if and only if the whole space is critical and every vector subspace is subcritical, where, here's the definition of subcriticality, the crucial concept. So a linear subspace V of the vector space RD is said to be subcritical if it satisfies this inequality. Its dimension is less than or equal to the specific linear combination of the dimensions of its images under the mappings. So we can think of the mappings as sort of projections, and we have these sort of generalized shadows. We take the dimension of each shadow and we add them up with coefficients equal to the reciprocals of the exponents Pj in the inequality. Okay? So a subspace is subcritical if this happens. It's critical if equality holds in this relation. Okay? And the theorem says that the inequality holds if and only if the whole space is critical and every subspace is subcritical. Okay? Criticality of the whole space is a scaling condition. Because it's a non-compact space, you can scale up, you can scale down. That ends up forcing equality. And the subcriticality is a kind of partial scaling, where you scale some of the variables and not others. Okay, there's a corresponding result for finitely generated discrete abelian groups. You replace dimension by rank, and you drop the criticality hypothesis in that case. Okay? All right, so there's a version for the discrete theory as well. Okay, so there's a nice characterization, which for some purposes is the end of the story, but you can go a little farther. So in this slide, we're going to take all the valid inequalities, all the combinations of exponents that work, and we're going to encode them by their reciprocals. The linear mappings LJ remain fixed here. They're regarded as given. We consider the set of all inequalities with those particular mappings that are true, and we encode them by the reciprocals of the exponents. And it's a consequence of the theorem in the last slide that the set that encodes them in this way is compact, convex, and it's a polytope. So it has only finitely many extreme points. Okay? By definition, it lies in 0, 1 to the n. We only consider exponents greater than or equal to 1, so the reciprocals never exceed 1. Okay? And the theorem here, by two different groups of authors, says that, some of whom were computer scientists, that theorem says that there exists an algorithm that computes this polytope. Okay? So that means it spits out a finite list of all the extreme points. The polytope is the convex hull of its extreme points. There are finitely many. It spits out a list. You can also specify a polytope by writing it as an intersection of half planes, and it spits out a list of inequalities that specify half planes whose intersection is exactly k. Okay? The theorem I just gave you, after all, says that k is specified by certain inequalities that define half planes. So it's possible to compute a list which will actually tell you what k is. Okay? All right. So that's fine. But there is a question one can ask still. One can try to compute a little bit more. You see, let me go back 2 slides. I've given you here a list of inequalities which specifies k. It's all these inequalities. For every linear subspace, you have an inequality. And the question now is, can you compute which of those inequalities actually arise? That is, if you were to go through all the possible subspaces, what combinations would arise for the rank, this is for the discrete case, what possibilities would arise for the rank of the subspace and the rank of its image? Okay? So now we want to compute not a list that suffices to define k, but the entire list of combinations of ranks that is actually realized for a particular example. And the theorem here says that an affirmative answer to this question, so one can compute all these things if and only if one has an affirmative solution to Hilbert's 10th problem over the rationals. Okay, so I'm not a logician, I'm not an expert in these things, so I needed to be reminded what Hilbert's 10th problem is, and I will remind you. So Hilbert's 10th problem asks, is there an algorithm which, given finitely many polynomial equations in finitely many variables, tells you whether the set of solutions is empty or non-empty? Okay? The problem is not to compute the solutions, it's just to decide, is the set of solutions empty or not? Okay? This question has variance because you can ask for solutions over the reals, over the integers, etc. So for the variant over the reals, it was solved in the affirmative by Tarski. It's a Berkeley theorem, almost 100 years ago. Most famously, for the integers, the answer is negative, as was shown in a whole series of works culminating in Matyasiewicz. But for us, the relevant case is the rationals. That's what I said on the last slide. And for the rationals, it's still open. There's been progress in the last year or two on the case where you're working over an algebraic number field. So there are other possibilities besides the reals and the integers and the rationals. The upshot for me is that, again, here's a subtlety that lies just below the surface. One can compute k effectively, but it's unknown whether it's possible to compute the list that defines k. I told you a theorem which said that one can compute a list that suffices to define k, but the whole list that actually specifies k, according to the theorem, we don't know. No one knows how to compute that. Okay. All right. There's an application to computer science. The work I did on this was partly in collaboration with some computer scientists and a logician, but I just don't have any time to go into that, so I'm going to skip over that. I'm sorry. I had really hoped to do that. Okay. So now we start with some results involving oscillation. So here's a class of oscillatory multilinear operators. My operator is T. It depends on a large parameter lambda, and it takes in n measurable functions fj. We have an integral over a ball or similar region. We have our oscillatory factor e to the I lambda p, and we have a product of n linear factors, which again are general measurable functions composed with mappings to lower dimensional spaces, always strictly lower dimensional. Okay? A new thing here is that for this little theory that I'm going to describe next, I'm going to always assume the phase is a polynomial, not just a smooth function, but a polynomial. That introduces purely technical simplifications in the statements. Okay, I'm also going to assume that each of the fj's is integrable. I'm integrating over a bounded region, so that certainly ensures that the integral is finite and well-defined. It avoids all the difficulties I showed you with the Diophantine question. Okay, so one expects a bound of the form negative power of lambda times the product of the L infinity norms. One expects that, but some hypothesis is needed. For instance, in the theory of multilinear oscillatory integrals, if the phase function is linear, then there's no decay at all. Okay, so there's some cases that have to be avoided. One has to have a hypothesis, and perhaps the first question in this theory is, what should the hypothesis be? What should be its nature? So here is at least an obvious necessary condition that you've got to assume. I define P to be degenerate relative to the given mappings. It's a property of P relative to the mappings if it's possible to write P as a sum of functions composed with the given mappings. Okay? I require the functions to be measurable. I don't require anything else. If you require them to be polynomials, it turns out to be equivalent. If you require them to be distributions, if you're really very generous, it's still equivalent. So it doesn't really matter exactly what you require of these. So let's say functions. Okay, so that's what it means to be degenerate. And a necessary condition for my inequality is that P is not degenerate. Because if P is degenerate, I can choose the f's to be e to the minus I lambda times these h's. And if I multiply them all together in the way I'm supposed to, and multiply by e to the I lambda p, then embarrassingly, the integrand is identically 1. It doesn't depend on lambda at all, and therefore it doesn't tend to 0. Okay, so if p is degenerate, there's no decay. Right. So this is a very simple business, but as far as I know, this was first looked at 20 years ago by Li Taotiel and collaborator, who asked, is non-degeneracy of P always a sufficient condition, or do you sometimes need to assume something else? Is there any other necessary condition at all? This is very obvious and very simple. And this is still an open question. I don't know a single case where any other condition has been shown to be necessary. So there's a very, very general statement here, which one might think is true. Okay? All right. So those authors proved 2 theorems, and here's one of them. This is for the case where the mappings map Rd down to R1. So the factors are all functions of just one variable. That's one extreme case. And it says that non-degeneracy is a sufficient condition provided there are not too many factors. Provided the number of factors is strictly less than twice the dimension of the space over which one is integrating. Okay? All right. There was a little additional progress. The same authors proved a second theorem, which I won't state. And Oliveira e Silva and I treated some cases where the target spaces had dimension greater than 1. But the theory remains very, very limited in scope. It's, to me, a remarkable thing. It's such a simple question, and so little is known about it. Okay? Earlier in the talk, I told you the go-to method for the linear case, and here it is. One can try to prove things via the go-to method of composing the operator with its adjoint, which just boils down to doing the Cauchy-Schwarz inequality. Okay? That's all it boils down to. Well, if you do that, it turns a trilinear form into a quadrilinear one. Things get worse. And it doesn't bring in any sort of scalar oscillatory integral. There's no inner integral where the measurable factors just go away. So this just doesn't work. And that's why one can't just settle this easily. So here is a bit of really infinitesimal progress. Suppose we're integrating over a space of dimension 3 or higher. The 2-dimensional case is trivial. Suppose we have mappings to R1, and the number of those mappings is exactly twice the dimension of the ambient space. So this is the next case that hadn't been treated. And there's a technical assumption here. If you write each of these mappings as a matrix, I assume that all the elements of the matrix are rational numbers. Okay? Without that, I can't prove anything. So there's an extra rationality hypothesis. So the theorem says, let P be a homogeneous quadratic real-valued polynomial. That's a big assumption, but there are lots of examples that were unknown where it's like that. So this is okay. P can be quadratic and still be non-degenerate. Then there is an inequality, but the theorem doesn't give a negative power of lambda. The theorem just says there exists a function of lambda, which tends to 0 as lambda goes to infinity, for which the bound holds. Okay? You ask me, okay, it's not a power, but how fast does it go to 0? I have no idea. The theorem's non-constructive. Actually, in principle, the proof does not give anything in particular. It's a non-constructive thing. Very, very unsatisfactory. Okay, I can't tell you very much about the proof, but I'll tell you about 2 ingredients. One comes from ergodic theory and is sort of Ramsey theoretic in flavor. The other is essentially sort of algebraic. So the proof relies on a theorem of Furstenberg and Katz-Nelson from 1978, which was about commuting measure-preserving transformations. So it's ergodic theory of several commuting transformations. This is not their theorem, but it's a consequence of their theorem, a special case of a consequence. So suppose we have the d-dimensional integer z to the d, and we have a finite subset. Suppose we have an infinite subset of z to the d with positive upper density. So that means roughly that if you take a very large cube and pick a point at it from random, the probability that it belongs to E is greater than or equal to some positive number. Okay? And that's in the lim sup sense. So there's a sequence of cubes getting bigger and bigger so that this condition holds for that. Okay? All right. So the theorem says that there exists an affine copy of this finite set S in the set E. Any subset of positive density contains an affine copy of an arbitrary specified set S. So this means that you get to dilate S by an integer factor k and then translate it by any integer amount n. And so there will exist at least one copy, and hence infinitely many, that lie in E. So that's the theorem of Furstenberg-Katz-Nelson, or a corollary of their theorem. So that's one thing that's used in the proof. So here's a connection with ergodic theory and with Ramsey theory. Another thing that went into the proof is what I call finite witnesses. So here's a general theorem about the nature of the concept of non-degeneracy. It says that if we have a bunch of mappings to a lower dimensional space, these are surjective linear mappings, again, all represented by rational matrices, they have to be commensurate in that sense, then if you have a non-degenerate polynomial phase, then that non-degeneracy is proved by some finite set. So there exists a finite set so that if you take that polynomial and restrict it to that finite set, even on that finite set, you can't write it as a linear combination of functions composed with the mappings. Okay? So there's a finitary obstruction to non-degeneracy. If you're non-degenerate, then there exists a finitary then there exists a finitary proof that you're non-degenerate. Okay, so at least this theorem sort of explains how you start to see how finite things in Ramsey theory might begin to come into the proof. Okay, and this theorem is basically an exercise in multivariable partial difference equations in the theory of Z modules. So again, there's a lot of algebra in the background here once you get into the multi-linear world. Okay? In this slide, I just remind you there's a long-standing relationship between oscillatory integrals and certain discrete problems. And as an example, I've chosen counting lattice points in a large ball. So you take z to the d, you take a ball of radius r centered at the origin, you take r very large, and how many lattice points are in there? Well, in the two-dimensional case, you should have roughly pi r squared lattice points, the area of the ball. And a good approximation, it's not what's conjectured and it's not the best that's known, but it's a pretty good result, is pi r squared plus O of r to the 2/3. So the exponent here is strictly less than 1. And this can be proved using this is a very well-known result. This can be proved using the Poisson summation formula and the asymptotics, the Fourier transforms of the indicator function of the unit ball. So that's an application of scalar oscillatory integral theory used for a counting problem. Okay? And the proof I just told you, its proof reverses this standard bit of logic. It uses a point counting inequality to get back to an oscillatory inequality. So it's the usual reasoning in reverse. Okay, so let me see. It's 3:16, and we started. 30. Okay, so I've been talking for about, I think, 40 minutes.
Yeah.
Okay. So good. So I'm talking a little faster than I did in Lisbon. Okay. So all this has merely been an introduction to what I call implicitly oscillatory multilinear inequalities. So now I'll try to tell you a little bit about those. Okay. All right. So here we're interested in scalar valued multilinear forms. We have t acts on f1 through fn, which are, again, just measurable. We have an integral over a ball or similar region in some space Rd. And our integrand is a product of factors fj, these are the measurable functions, composed with mappings to a lower dimensional space. The changes here are twofold. First of all, I'm no longer requiring these mappings to be linear. Now they will be just very smooth. I'll assume real analytic, but definitely not linear. The other thing is that the oscillatory factor is gone. There's no oscillatory factor at all. Okay. There's a little, the remark here says the following thing. You can, if you have such an integral, you can always think of it as an integral over some subset of the product of the domains of the fj's. After all, what goes in is the fj's. So it must be some kind of integral over the product of the domains. This is, at least formally, if I have real analytic mappings, an integral over some analytic variety sitting in the product of the domains. And I'm always really assuming that that variety has positive codimension. So I'm definitely not integrating over all the possible combinations of arguments of the various variables. Okay? We're allowing some interactions, but many interactions between the various fj's are not allowed here. Okay? So that makes it singular in a certain sense. Okay, so there's no oscillatory factor, and the mappings phi j are not assumed to be linear. Those are the changes. So where's the oscillation? The oscillation lies in the goal, in the formulation of the inequality that we're going to try to prove. I don't want a bound in terms of Lebesgue norms anymore. I want an upper bound in terms of a product of Sobolev norms of negative order. So if you're not familiar with Sobolev spaces, I'll give you an alternative formulation on the next slide. But I want a bound in terms of negative order Sobolev norms, W infinity comma S. The precise definition of Sobolev spaces is not so important. Basically, any definitions will give you an equivalent inequality. But the point here is I want negative norms. So that allows the functions fj to be singular in various ways. Okay? So one application of such an inequality is that it would simply tell you that certain distributions can be multiplied. We're talking here about things in negative order Sobolev spaces, so they're distributions. And here I'm plugging them into an integral, and I'm integrating. So I can integrate over b, or I could integrate with respect to a smooth cutoff function. And if you think of this in terms of integration with respect to a smooth cutoff function, then I'm saying that that product, that integrand, is a distribution. So I'm really saying here that the product of distributions of a certain type is well defined as a distribution. It's a theorem that says you can multiply distributions. I'm not specifying the order of those distributions. And in fact, I just want to prove that there's some negative order, minus 10 to the minus 10. I mean, very close to 0. But I want to know that there's some negative order for which I can do such a multiplication. Okay. So another way to say that is this. The goal brings oscillation into play. Another way to formulate it is to assume that at least one of the factors has a Fourier transform that's supported only at high frequencies. So by Fourier inversion, every one of my factors can be written as an inverse Fourier transform of some function. I can think of it as superposition of waves, and I'm assuming here that for at least one factor, all the waves in that superposition have very high frequencies, so very short wavelength. Okay? So if you have a wave with very short wavelength, you have a lot of oscillation over very small scales. And that's the real assumption here. And you can formulate that in lots of ways. It's not important how you do it. Okay. So here it is given that at least one factor oscillates rapidly, but the change is there's no assumption about the form of that oscillation. I'm no longer saying is e to the I lambda p where p is given. Here, I'm simply assuming there is a lot of oscillation everywhere in one factor, but no assumption otherwise about the form of that oscillation. Okay. And once again, there's a relatively obvious necessary condition for such an inequality. Before it was called non-degeneracy, now it's called non-resonance. And so we define its negation resonance. So my tuple of mappings, boldface phi, is said to be resonant if there exist real analytic functions gj in some open sets, some connected open sets, at least one of them non-constant, that satisfy this linear relation. When I sum the GJs composed with the mappings, I get a function that vanishes identically. Okay, and possibly in some small open set. Okay, now that's easy to solve. You choose all the GJs to be 0, but I have a requirement that one of the GJs is non-constant. Okay, so that's ruled out. Another way to solve it is to choose them all to be constants and choose the constants to add up to 0. But again, I'm ruling out that trivial solution. Okay? This should remind you of the condition for non-degeneracy of a phase. That was an inhomogeneous equation. This is the homogeneous version. I don't have a phase here, so I just replace the phase by 0. But otherwise, it's the same condition. Okay? All right. And that's resonance. Non-resonance is its negation. And non-resonance is obviously a necessary condition. The inequality is false if phi is resonant, because I do the same construction. I choose fj to be e to the I lambda gj, where lambda is a large parameter, which I now bring in, and gj are solutions of this equation. And then, if I do this, my integrand becomes constant on some open set. And therefore, again, if I integrate, the integral does not tend to 0 as lambda goes to infinity. But one of these does oscillate. The non-constant one oscillates very fast. So that satisfies my conditions. Okay. So a pretty bold conjecture, in analogy with the last thing I told you, would be that an inequality of this type holds for real analytic mappings, provided we have non-resonance, provided the obvious necessary condition is satisfied. If you're really brave, you could conjecture that such an inequality always holds. So that might be true. I certainly don't know any counterexample. If you're a little less brave, you would say, okay, maybe I don't get a negative power of lambda. Maybe I get some function of lambda that tends to 0, maybe very slowly, e to the minus e, some exponential tower or something, or log, 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 or one of those things. But some function that tends to 0 as lambda goes to infinity. Okay, that also would be interesting. Okay. So that would be a conjecture, that would be a goal here. So far as I know, the first case of such an inequality to be treated was done by Bourgain in 1988. So he considered 3 mappings from R2 to R1. My coordinates in R2 are x comma t. One mapping sends x comma t to x. One sends it to x plus t, and here's the nonlinear one, sends it to x plus t squared. Okay? And in a couple slides, I'll tell you the specific application. For him, this was a lemma in pursuit of a theorem, and I'll tell you what the theorem said soon. Okay? Properties. First of all, the necessary condition is satisfied in lots of cases. In any reasonable sense, a pair or triple or quadruple of generic mappings real analytic mappings does satisfy the non-degeneracy hypothesis. It's not a special thing. It's satisfied generically. Second, it's fully invariant under real analytic diffeomorphisms. You can change variables in the domain of integration. you also have mappings to other spaces, and you can change variables in those spaces. So it's invariant under a combination of all such diffeomorphisms. Okay, so here's the theorem. It's a very modest theorem. It's about the case where we're integrating over a two-dimensional region. We have mappings then to a lower dimensional space, which is R1, and we have either 3 or 4 factors. 2 factors is trivial. 3 is the first non-trivial case. So the theorem is only in this low dimensional case, only with 3 or 4 factors. I've been working on 5 factors for a long time, and I can't do it yet. So this is really a limited theorem. Okay, so the theorem says if we're integrating over a ball in R2 for functions of 1 variable of 3 or 4 factors, if we have a non-resonant datum, then the inequality is true. There does exist a negative S. There does exist a constant, so my form is majorized by a product of negative order Sobolev norms. Okay? This in principle is effective. So in principle, you could calculate an S out of the proof. It would take some work, and it would be incredibly close to 0, but it is in principle an effective proof. Okay, so again, the proof of the case of 5 factors is already very much open. So lots of people have contributed over some period to this kind of thing. At first, it was a rather obscure thing, and there was very little work on it. There was a paper of Bourgain in 1988. There was an Annals of Mathematics paper by Joly, Métivier, and Rauch in 1995. They're experts in nonlinear partial differential equations. Their perspective was that of compensated compactness, and they had never heard of Bourgain's paper, which was also somewhat obscure. They didn't know he had done one case already. And then I got involved in this much later, and then there have been a few other works subsequently. So here's one application. This is why the PDE people were interested in this. It's an application to weak convergence. So if you have a case where the inequality is true, and if you have a sequence of tuples that are uniformly bounded in, say, L infinity, and if you have weak convergence of the factors as functions in R1, then this product, so this is a function in R2. This product will converge weakly to the product of the limits. The limit of the product is a product of the limits, but you only need weak convergence of the factors. Okay, so this is, of course, something that's not true in general for weak convergence. If you have e to the I n x in R1, as n goes to infinity, that tends weakly to 0. If you have e to the minus I n x, then as n goes to plus infinity, that goes weakly to 0. But the product is identically 1, which does not tend weakly to 0. So weak convergence is actually a continuity of weak continuity is actually a very rare thing. And a corollary is for functions of this particular form, it holds. Okay, so that's good. Okay, Joly, Métivier, and Rauch proved this. They didn't prove any inequality. By functional analysis, this weak convergence holds if and only if there exists a true inequality with something tending to 0, like some function of lambda. But their proof also was non-effective. It used a compactness step. So they didn't get any particular inequality. Okay, here's another kind of application. It's in the spirit of Semeretti's theorem. Bourgain had considered a sort of nonlinear continuum version of Semeretti's theorem. And this is a generalization of what Bourgain did. So we have either 3 or 4 factors. We have a subset of the interval 0, 1. That subset is measurable and has positive Lebesgue measure. We assume that the datum is non-resonant in the sense I defined. We also have an assumption that there's now one of the indices j is 0. Phi sub 0 of x comma t is x, and phi sub j of x comma 0 is x, of x comma 0 is x when j is not equal to 0. So that sort of says it's like looking for configurations which contain a specified point x, and as t tends to 0, the diameter of those configurations shrinks to 0. Okay, when t equals 0, everything collapses and we're looking for configurations where all the points coincide. Okay, that's what the assumptions say. And the conclusion of the theorem, and this sort of argument, and this sort of formulation, the sort of argument was developed by Bourgain, is first of all, you have configurations of a specified kind in E. That is, there do exist points y comma t in R2 so that each of the phi j's maps that into E. So this allows us to find specified configurations of 3 or 4 points inside the set E. You know, in Samaretti's theorem, you look for maybe arithmetic progressions of length 4 in a discrete set. This is the same kind of thing, but we're in a continuum world, and we're looking for progressions that are not arithmetic in nature. Okay. Everything I've said so far, the conclusion is trivial by Lebesgue's density theorem. If you want to find small enough configurations, you can always do it, because Lebesgue's theorem says that if you look in a small enough region, almost all the points belong to E at a point of density. But the theorem gives a quantitative lower bound, which depends only on the measure of E. It doesn't depend on the nature of E. And the Lebesgue differentiation theorem is completely non-quantitative. So there exists a t greater than this incredibly small quantity, but a positive, so that this configuration lies in E. So you can find finite point configurations whose diameter is bounded below by a certain function of the measure of E. Okay, so this connects to another topic. I was lucky. I happened to be in Berkeley on a day when Professor Chern was giving a lecture. And this was the topic of Professor Chern's lecture. It was 3 webs and their curvature. And 3 webs come into the story now. So a 3 web in an open subset of R2 for simplicity is an ordered triple of smooth foliations with pairwise transverse leaves. So I'll draw one. Oh, geez. I'll draw one if I can find an eraser. In a 2-dimensional region, a smooth foliation just looks like this. You have a family of curves. They fill out the whole space. No 2 intersect one another. Each curve is smooth, and they sort of smoothly fill out the space. So that's a foliation. Here's another foliation. These 2 foliations have the property that any 2 leaves meet transversely. Okay? And a 3 web simply consists of 3 foliations superimposed on one another. And I try to draw that, it'll look worse, it won't be more revealing. Okay? So for a 3 web, you simply have 3 such foliations with the condition that any 2 leaves meet transversely. Okay? A good example is what I call the Pedro Nunes, which I can't pronounce correctly, 3 web. So you take an open set on the surface of the Earth. You take the lines of longitude coming down from the poles. You take the lines of latitude. And then you consider the lines that a navigator would follow if the navigator were to always cross lines of longitude at a constant angle, so say 15 degrees. You cross all lines of longitude at a constant angle, and that defines a 3rd foliation. I'm sorry? Rum lines, exactly. They're called rum lines. The curves are called loxodromic spirals or something. And this was studied by Professor Nunes. Yeah. So that gives you actually an example which has a very nice property, which I'll come to. Okay? So that's a 3 web. A 3 web can also be defined by a triple of mappings. If you have mappings, then you define the curves to be the level sets, the sets along which the mappings are constant. So 3 mappings is a way to describe a 3 web. But a 3 web doesn't necessarily come with a parameterization, and there are lots of different mappings that will describe the same 3 web. Okay, a web is called locally linearizable if there exist smooth changes of coordinates that transform all 3 foliations to foliations by families of parallel straight lines. That's the linearizable case. Okay, and a good example of that is the Pedro Nunes foliation. If you take the surface of the Earth and you take the famous Mercator projection, that turns all the lines of longitude into vertical line, constant longitude to vertical lines, all the lines of constant latitude into horizontal lines, and it turns the rum lines into another family of parallel straight lines. Okay? So the Nunes web is linearizable. locally. Okay. A three-web has a curvature. The quickest way to define that is to change variables. So the first two mappings are just coordinate mappings. Then you define a function theta. You take the third mapping and you take its first partial derivatives, take their ratio. And the curvature is, algebraically, it's a little complicated. You have to take that theta, you take its logarithm, you take a certain second order partial derivative. That defines the curvature of the web. It's a certain nonlinear expression in up to third derivatives. And it has nice invariance properties. It's a diffeomorphism invariant quantity. So it doesn't depend on the way the web is parametrized, and it's invariant under diffeomorphisms. Okay, and this gives you another way to look at the non-resonance hypothesis that I mentioned. Non-resonance is equivalent to non-linearizability of the underlying web, which is equivalent to non-vanishing, the curvature not vanishing identically. Okay, so that's a nice connection. It doesn't help you prove anything, but it's certainly a nice connection. Okay, so let me see where I am on time. I started.
1 hour.
Yeah, okay, excellent. So I am done. I don't think you really need to hear much about the proof right now. Let me just skip ahead. Okay, good. So to summarize, inequalities for multilinear oscillatory operators do arise in a variety of contexts. They have intriguing connections with a variety of different concepts, both in their formulations and in their hypotheses and in their proofs. Tricky non-analytic issues arise right below the surface. There are lots and lots of open questions. One doesn't know very much about the questions I've discussed. Okay, so thank you for your attention and for the honor of delivering these lectures.
According to thing called. So any questions, please send them.
Yeah, thank you very much for this interesting talk. Did you think to extend your technicality to another transform? For instance, mailing transform, mailing convolution with a portion of variables instead of difference. Is it possible to because it's a good relationship with special functions and Riemann zeta function, some kind of results to extend on this topic.
So this kind of theory is pretty much all the things I told you about are set up so has to have a certain diffeomorphism invariance. And so at least in a local version, it doesn't really matter whether one looks at Fourier transform or Mellin transform. Those end up being the same under changes of variables.
For convolution also you have instead of difference portion or some kind of results to apply the Mellin convolution theory. For instance, if you take your slide, please, 15.
15. Oh, I'm sorry. The only way I know to go back is to one at a time.
Okay. So when you add some one multiplier to your convolution.
15.
Maybe previous. This one. Yeah, next. Now 14.
14.
14.
Yeah, that convolution with Young convolution inequality. Then you can consider also Mellin type convolution with this kind of three functions. And I think it's possible to extend your theory with this kind of operator. This is kind of question because we are working a lot with kind of machinery.
Yeah. So certainly one can simply make an exponential change of variables and convert one to the other. Do you have?
But this is good consequence for special functions, hypergeometric functions.
I see.
Like kind of Bessel, Hankel transform, etc. This is a really deep relationship.
And then it comes to Riemann zeta function. So it could be done maybe some new feature for Riemann zeta. Riemann hypothesis. And another question.
Yeah.
What is about some kind of van der Kolk inequality generalization? Did you involve some kind of?
So you're thinking about now about exponential sums.
Yes.
Yes, I have not thought about that. And so some of these
I
things.
think it's kind
Yes.
of Wiener classical works. It's related to no say. I didn't know whether it was generalized or not.
So some of these things could have exponential sums. Things that would be even harder, and I'm having so much trouble with this.
We are working a lot with such patterns.
Yes, yes.
And last question, please. This Young convolution, if you use over integration over y, if you use Parseval for Fourier transform, so you come integral
That kind of A to D, if you apply Parseval equality by y, then you get G Fourier and H or something, maybe different feature can be done. I'm thinking.
Yeah. So there is probably related to this question, there is a theory about the relationship between these kind of inequalities and the Fourier transform. Yes. And in this case, of course, if you take Young's convolution inequality, that's related by the Fourier transform to the Hausdorff-Young inequality.
So I mean, instead of integral by y, I write in terms of Fourier, G and H.
Yes.
And then you have R to D, different integral. So
Yes.
some kind of probably.
Yes. So Jonathan Bennett and his collaborators have and Michael Cowling and others have looked at putting the Fourier transform into these sorts of things.
My student
Diogo, so we discussed Diogo Oliveira. So I discussed with him such kind of stuff. Thank you.
Yeah. Okay. Thank you.
Okay. More questions? Well, you mentioned some ergodic connections with Ramsey theory.
Yes.
They were mainly used to prove oscillatory inequality. Is there other way around, some application to ergodic theory of these powerful techniques?
Not that I'm aware of. The ergodic theory seems to be a better point of view for non-effective results. I'm thinking now rather about taking out the ergodic. Diogo and I have talked about taking out the ergodic theory part and putting something more quantitative in, and with more information in its place. I think that's the direction that we're going to pursue. Yeah, we want to get rid of the connection is very nice and it's suggestive, but what it suggests is we should avoid the ergodic theory and use certain other techniques in its place. Yeah.
Okay.
Yeah. Just as Gowers made significant progress on Semiretti's theorem by making everything more quantitative. And I think that's the direction.
Okay. So one last question. You put us a lot of open questions. Is there one that you think that is not so open anymore, or that you're working on and you think you'll get some results soon, or are all very hard?
I'm hoping to make some more progress, possibly to. For instance, I have some hope of doing the last theorem with 5 factors, getting not a power law, but just getting some very slow gain. But it's very unwise to even suggest the promise of something in public that's not done. So I'm merely trying. That's all I'm merely trying.